7.4, we're going to talk about the length of curves. We introduced this idea on Friday. So when we think about a sine curve is like this. There's two different ways we can define the length of this curve. There's what we can define as being the wavelength of the curve, which is otherwise in trig terms known as the period of the curve. And that is just the horizontal distance of how far it takes before the cycle starts repeating itself. Okay? So for a normal sine curve, that's 2 pi. When we talk about like waves, like true wave patterns in a body of water, like an ocean or Lake Michigan, the wavelength is the horizontal distance between the waves. Okay, they're not actually measuring how high those waves are going. That's a different measurement. It's called our amplitude. Okay, so the wavelength is the horizontal distance of a curve before it starts repeating itself if it's a periodic type curve. The curve length is the actual length of the curve itself, like taking a string to lay along the curve and then straightening out that string and saying how long is it going to be. Okay? So for sine, we can say it's definitely going to be longer than 2 pi because straight across would be 2 pi. If I trace that out with a string and then pull that string tight, it's going to be longer than that 2 pi. So our question is, how much longer? How do we find how much longer?
Take an integral.
So we're going to take an integral of something, but it's not just going to be an integral of the function. So we could, and we looked at an example of this on Friday, think about breaking this up into some triangles. We'll break it up into 4 triangles because that's convenient. Because of the symmetry of this curve, those 4 triangles will all be exactly the same. Okay. So going over is going to be a distance of pi halves. The vertical height of those triangles is going to be a distance of 1. And Pythagorean theorem will tell us that our hypotenuse is then going to be the square root of 1 squared plus pi halves squared. And we're going to have 4 of those. Okay, because all 4 of those triangles are the same size because of symmetry. That's an approximation. Okay?
Where'd you get the square root from again?
Pythagorean theorem.
Okay.
A squared plus b squared is c squared, so then I took the square root to undo the c squared.
Okay.
It's going to be an under approximation because those straight green line hypotenuses, hypotenusae, are still kind of a shorter length than the curve that goes around them. Okay? So it's going to be an under approximation. We could get a better approximation if we took smaller and smaller and smaller differences in our x's to get more and more and more triangles in there.
Will you ever have an over approximation?
No.
Okay.
So then we looked at thinking about a triangle as being a change in x and a change in y. Pythagorean theorem gives us a hypotenuse then of change in x squared plus change in y squared and square root of that for our Pythagorean theorem. Then we said what we would want to do is add up all of those, and our integral is our fancy adder. So we're going to add up all of these little hypotenuses of the different triangles that we get. If we are using a function that is in terms of x, then the derivative of x is just 1. And the derivative of y is the derivative of the y equation. And we would be going then from some point to some other point.
Can you do that again?
Yep. So I'm just taking this hypotenuse, and we're adding them all up. Our adder is our integral. Just like when we were talking about finding the area below the curve and we wanted to add up all those rectangles, we learned the best way to add up infinitely many rectangles is with an integral. So we're going to add up or integrate all of these hypotenuse lengths, the square root. But if our function is in terms of x's, so like if our function is y equals sine of x, then the derivative of x is just 1. So dx is just 1. The derivative of y is the derivative of whatever our y equation is. So that's what we've been calling dy dx or y prime. Okay? And then we're going from a to b from some value to some other value. So in this problem, if I want to find the length of one period of the sine curve, we would be going from 0 to 2 pi.
So when you have from A to B and from C to D, is that talking about where the curve is above the x-axis and below it?
No, those are the ends of the endpoints of the length that we're trying to find. So like in this problem, A would be 0 and B would be 2 pi.
Okay.
C and D would not work so well for this because C and D are if we change things to being in terms of y instead of terms in x.
Oh,
And then both of those y values would be 0, so it'd be 0 to 0, which isn't really going to be
that's
something
what
that
you
would
use
work out well
C
for
and
us.
D
Yeah.
Why do we use triangles rather than like a trapezoid?
Because triangle and a trapezoid would do the same thing because all we're caring about is that diagonal piece.
Okay.
So, I mean, I can draw whatever shape I want. I guess essentially here it is going to turn into a trapezoid because I'm going to kind of lift it off the curve. But all we're really caring about is that hypotenuse piece. And so it doesn't really matter whether we're looking, because we're not finding an area,
Okay.
we're just finding a length.
Okay,
As a
there we
podcast,
go.
why we don't use a parabola, then I realized we don't know the length of parabola, so
We don't know the length of a parabola. We
we
need
just
to
end up
integrate to
doing-
find that too.
We just end up
So
doing the exact same.
that won't work either. So for this example then, for sine of x, we would need to know then what is dy dx, or the derivative. So derivative of sine is
Cosine.
cosine. So then our formula for length is going to be the integral of, we're going to go 0 to 2 pi, square root of 1, the derivative of x is just 1, plus the derivative of our curve squared, dx. And this is a finenter.
I was gonna say,
Well, how
will
does
most of these be fininters, or?
Yes.
Okay.
The book only takes it to 2 decimal places, so I don't know what it is to 3, but
the why would dx equals 1 be pi halves?
if I was using those triangles, then dx would be pi halves. But what I'm trying to do is say, instead of using those triangles, which give me some error because they're not perfect, I want to take as small of a change as possible. And so dx is designed to be as tiny, tiny, tiny of a change as possible. And then that will give us the actual value of the curve. So like these little black triangles that I drew in there, those are like little tiny. They still wouldn't be perfect. There would still be some error in there. So we're saying let's make it as tiny as possible, and that's what we call dx.
Okay.
Excuse me. Between pi and 2 pi, though, the curve goes underneath the x-axis. Would that have anything to do
Length
with
is still positive length, whether it's above or below the curve. So good question. Area would be
Yeah.
positive or negative above or below the curve. Length is positive no matter where it is because I'm
Okay.
tracing out the entire thing with one string.
Okay.
So it doesn't matter where that string is.
And we're squaring any negative numbers.
Right.
See.
All right. So then the next part of our notes tell us that this works only if our curve is smooth, which means it has a continuous derivative, that there are no points of non-differentiability in here. So if we end up with corners or cusps or vertical tangents, this formula will not work for us. Okay. So we need to make sure that our curve is smooth, no corners, cusps, or vertical tangents. Because those happen at places where we can't take a derivative, and this formula requires us to take a derivative. Okay? So if we try to take a derivative of something we can't really take a derivative of, we're bound to get a wrong answer in that.
Oh my.
Okay? There are 2 forms
Dorothy.
of the length of the curve here. Okay? They are really exactly the same, except we use one if we have x's in our equations, and we would use the other one if we have y's in our equations. They're really the same thing though. We're going from endpoint to endpoint, whether we call it A and B or C or D, endpoint to endpoint, square root of 1 plus the derivative of the curve, whether it's in terms of x's or in terms of y, squared. Okay?
That's a formula for every time.
Every time. Well, unless we have those corners, cusps, or vertical tangents.
Oh my.
All right, example 2. Example 2 says find the exact length of the curve. That means that this is not going to be a finite question because finite will likely give us a decimal approximation, and it tells us here we want exact. These questions will often be finite questions because typically it's going to end up really gross. with having a square root and something squared underneath it. It won't usually cancel out nicely.
This one already
So-
starting to look really gross.
Usually, the problems will be finite. We talked about it a little bit before in our volume problems, how a lot of times when the question looks extremely intimidating, once we get into the formula, it actually really cleans up and becomes a possible thing to do then. Whereas if you take something that looks really pretty clean in the beginning, it becomes almost impossible to do by hand. Same type of thing is going to happen on these. If it looks really disgusting in the beginning, likely once we take a derivative and square it, it's going to clean up pretty nicely. As opposed to if it's nice and neat, take a derivative and square it, it's going to usually cause us some problems. Okay. So on this one, to use our formula, we need to know our derivative, or our dy dx. So we would multiply that 3/2 down and lower the power by 1. And the derivative of -1 is just 0, so that doesn't change anything there. I'm going to reduce this. So I end up with 2 square roots of 2 x to the 1/2. Our arc length formula is then the integral of from a to b. So they gave us the endpoints there. We're going from 0 to 1. Square root of 1 plus our derivative squared. So now when I square this thing out, when I square out 2 squared root of 2, I need to square the 2 and get 4. Square the square root of 2 and get 2, so I get 8x dx.
That's so nice.
And it ended up cleaning itself up really pretty nicely here. I'm going to rewrite this instead of a square root as 1 plus 8x to the 1/2 so that I can think about my power rule for integration. So when we integrate, we raise the power and divide by that new power. And I need to multiply by 1/8 on this problem to account for the chain rule that would happen inside of those parentheses. So if I took a derivative of this thing, I would do my power rule, but then I would also need to multiply by an 8 for the chain rule. So to undo that, I need to multiply by 1/8 to undo that chain rule. So I end up then with 1/12 of plug in 1 minus plug in 0. And I get 1/12 of 8 to the 3/2 minus 1/12.
Don't you get 9? 1/12, 9.
9 to the 3/2, thank you. To evaluate 9 to the 3/2, I do the bottom first. Remember that fraction exponent is really saying we're doing a square root of 9 cubed. I don't know what 9 cubed is, so I'm going to do a square root instead. So I take the square root and I get 3, and then I cube it and get 27. Yeah, it doesn't matter which one you do first. And so then I get 27/12 minus 1/12, which is 26/12, or 13/6.
It's a lot of reducing.
Look at the. Listen, I just do this with calculator.
And this is a case where on your homework, if it says something about analytically or exact, that means by hand without a calculator. And again, the answer keys by this point, I give them to you, and it's a good thing to check your answers, but they are a little bit lacking in the amount of work that they show. Because they expect that you remember all of the integration stuff and simplification stuff that we've done before, so they make a pretty big jump there from setting up the problem to getting the answer.
Could I go into my locker and get my book?
The next part of the notes says vertical tangents, corners and cusps. Oh my, yes, I have a Wizard of Oz reference there.
That's so good.
Never seen it.
We gotta.
You seen Wizard of Oz?
The whole class. The whole.
I'm glad that noise was just recorded, so I can listen back to my sound of shock anytime.
The whole class stopped.
What?
How was that recorded?
Recording lessons for student communication.
I have to watch the one from Friday still.
Can they hear us or not? You can hear her.
Yeah,
Alright, so in this we're just gonna do 2 examples and look at, we can't just blindly, anytime we're asked to find the length of a curve, do the arc length formula. But often, even if there is a problem with the derivative of a function, there's a way to get around it. Okay? There's 2 different ways that we can get around it, but you should not just apply the arc length formula blindly. So our first question is, we're going to look at the length of y equals x to the 1/3, and it tells us between the points -8, -2, and 8, 2.
Ooh, this could be a vertical tangent.
This is going to be a vertical tangent. If we graph out this curve, it looks like this. This is what our cube root function looks like. And so right there in the middle, mine probably isn't even quite extreme enough. We really have a vertical tangent where it stands right up. Okay. We can see why this is if we start to take a derivative. So if I take a derivative, dy dx is 1/3 of x to the -2/3, which is the same as 1/3x to the 2/3. If I plug in 0, I have a problem with that derivative. And 0 is within the range that we're looking at, so that's a problem. Okay? If we were trying to find the length of some other part of this curve that didn't include 0, we would be fine. But since we're trying to include 0 in there, we can't actually plug 0 into this derivative. That's a problem. So what we are going to do is change our variable of integration. So instead of thinking of our curve as being y is equal to the cubed root of x, we're going to think of our curve as being x is equal to y cubed. It's exactly the same thing. I'm just solving for the other variable.
Does it not? Oh, because now it's got a horizontal. Okay.
So now if I take a derivative, dx dy, I get 3y squared, and that derivative has no problems at all. So then for our arc length formula, we're going to integrate. Since we are going to have y's in our problem, we want to choose the y values from our points. So we're going to go from -2 to 2. Thank you. Right? If you have x's in the problems, you want to use x's as your limit. We're going to have y's in the problem, so we want to use the y's as our limits.
Yep.
Square root of 1 plus our derivative squared dy.
Do you square both the 3 and the 2 when you put it in?
Yes.
Okay.
You don't square the 2. You
You
multiply power to a power.
Yeah.
So this is going to be 1 plus 9y to the 4th.
In this case, it's no different, but
Sure.
every other
Right, but that's why I wanted to clarify that we're not actually squaring
I knew what I was
power to
thinking.
power. This is a fininter. So we get about 17.26. Again, the book only goes to 2 places, but AP you should always go to 3.
Dun dun dun.
If you don't notice that this curve has a problem and you just try to do the original setup and you work it through with the arc length formula with the x's in it and you finint it, it's kind of a mystery what you're going to get on your calculator. It might give you an error, okay, which would hopefully make you think, oh, there must be some sort of a problem with this function. Or it might give you the right answer, bonus, or it might give you a wrong answer. And it really could vary person to person sitting next to you. And it's all something weird in the way that calculators are set up. And you would think they would all be set up the same way when they leave the factory, and I could tell you exactly what your calculator is going to do. But it really is kind of a mystery as to what your calculator is
Yeah,
going
can
to
we
do.
all do it?
Sure.
It's kind of important because if you know you're gonna. I want to see what the cat says.
So to do that, we have to think about what our setup would be then.
Low batteries.
It's only giving
I know.
to the second.
You've been
There's a
telling me
zero.
that since algebra 2.
That was the last one too. There's a 0 after the 6. That's why I was.
Yeah.
Oh, okay. So if we do arc length in terms of x's, then our formula would be integral -8 to 8 square root of 1 plus our x derivative, which was the 1/3 x to the -2/3 squared dx. So that's what we would want to put into our calculator. If you want to put in fewer parentheses, you could square this thing out. And I mean, I wouldn't, if your calculator gives you the right answer, I wouldn't say like, awesome, I never need to think about this. It might give you the right answer here and a wrong answer on a different problem. Okay, and really what it boils down to is the algorithm that the calculator uses is it's basically finding those right triangles and adding up a whole lot of those right triangles. So it's using a really tiny dx and doing like we did in that first example. It's just doing a lot of triangles. So the thing is, if the algorithm it's using lands right on the point that's a problem, then it'll tell you I have a problem. If the algorithm it's using kind of skips over that point, then it won't realize there's a problem. So it really can vary question to question even whether it's going to give you a right answer or a wrong answer here. So, did it give you an error? Yep.
You got negative for the x.
How do we get an answer?
Why?
You have to change
Yeah.
Then
Here, you have to put it into x
We don't square the exponent, we multiply. So, oh, you're saying it should still be
You
negative.
don't
Yes,
use the,
thank you.
the y equals
Yeah.
sign,
Just get
you use
errors.
the x equals sign.
Mine's going into
Yeah,
the
that should
infinity
still be
loop.
negative.
Oh,
Yeah,
God.
so, yeah, but on when you.
I should never define.
Darn it.
Can we?
Yep, mine just
You have
keeps
to use
going.
the y limits.
It's just thinking.
Yep.
It's stuck in a loop.
Nope, give me an answer.
A right answer or wrong answer?
Wrong answer. 20.99. Unless I typed it in Daniel.
So-
Daniel, I typed it in wrong.
Moral of the story is once you take your derivative, always consider whether that derivative is going to have any problems within the interval that we're looking.
I thought the negative stories that calculators are now individuals.
Last example.
That y.
They don't put x to derivatives.
This is kind of a corner.
Mm-hmm. Alright, so this function has an absolute value in it, which is going to end up giving us a corner. We could graph it on the calculator if I wanted to think about what this thing is going to look like by hand. I think we could all use a little bit of practice in thinking about what absolute values do to things. This is really going to create a piecewise function that is going to do one thing if x is negative and another thing if x is positive. At 0, when x is 0, it'll be doing exactly the same thing. So it's going to do one thing when x is positive, one thing when x is negative. X is positive is the easier case because if you take the absolute value of a positive, it doesn't do anything to it. So if I take the absolute value of a positive, then I would get x squared minus just 4x minus x. Or I could rework that to say minus 5x. Okay? So if you take an absolute value of a positive, it's just like the absolute value isn't even there. If you take the absolute value of a negative, it's giving you out a positive. Or it's giving you out the opposite of your input. So opposite in math means negative, so we want to change the sign of that term only. Okay? If I put in a -2, it's going to give me out a +2. So then I would need to change the sign of the 4 to account for the change of the sign of my x. Okay? So then I end up getting x squared plus 3x. So what this thing is going to look like is two parabolas that come together when x is 0 with a value of 0. And it's going to look something like this.
Oh, and that's, is that a corner or a cusp?
So that it's a corner technically, but it's kind of cusp-ish looking.
It's
But
hard to
it's
tell.
technically a corner. A cusp is distinctly that the slope is becoming infinite.
Okay.
So the
negative.
slopes on the two sides are both values that we could evaluate. They're not infinite, so that's why it's a corner and not a cusp. It's just a rounded corner. Whereas a cusp, if we were trying to evaluate those two slopes, they would be infinite. So to evaluate then the length of this curve, what we need to do is evaluate the two individual lengths. So I'm going to take my y equation and take a derivative of it. Piecewise means I need to take the derivative of each piece then. So 2x plus 3 and 2x minus 5. Now, in my original function, I should have an equal to bar on one of those two, and it doesn't really matter which one. But in the derivative, I should not have an equal to bar on either one of them because the derivative does not exist when x equals 0.
Okay.
It doesn't?
Because we have a corner.
That's right.
So then for arc length, for the first piece, I'm going to do the square root of 1 plus 2x plus 3 squared. And that's going to go from -4 to 0. And I want to add that to the positive side piece. And once again, it's a finiter.
You said they won't take off if we forget the dx, right?
Yes, if you are asked in a free response problem to set this up, you will not get deducted for neglecting to include the dx.
Because they assume you have it.
They said because there's only 9 points to be given, and that seems extreme to take 1 point away for forgetting to write something so small.
And because you can go without
It's not technically insignificant. Without it, you really can't take an integral.
Is
I
there
mean,
a-
you have to be saying what value you're taking your integral in terms of. So really, without it, it's not actually possible to integrate. But since it turns into a more notational thing, they don't take off for that notation.
We've never thought that you might be a little
All right, so your homework is from section 4. All right, our first question says, assume the acceleration changes linearly in each 10-second time interval, and that the velocity at time 0 is 3. So the velocity of 0 is 3 meters per second. Show how the velocity can be calculated at time 10. So if we have acceleration data and we want velocity data, what do we need to do? Integral. So it says, how can we calculate the velocity at time 10? So that's looking at our first interval from 0 to 10. And we can plot that point. We got a point at 0, 5. And we have a point at 10, 12. And it says assume that we have a linear change within that interval. So if we want to integrate, then visually what are we doing?
Area underneath.
Finding the area underneath, which is the area of a trapezoid. The area of a trapezoid is?
One half base. Height 1. Height 1.
Base.
Minus height 2.
Height times.
No,
Length.
height 1.
We're doing it. Wait.
I think you're saying the right thing. Some of you are saying it sideways, some of you are saying it up and down.
Base 1,
Typically
base
we
2,
say
height.
base 1 and base 2
Oh,
and
base 1,
height.
base 2.
We kind of think of this on its side though, so some of you are saying like height 1 and height 2, which is okay as well. But we're going to add up the 5 and the 12 and multiply by the length of that interval, which is 10, and then all that times a half. So that gives us 17, 170, 85.
Wow.
Now what is that?
That is velocity.
Change in velocity.
That's the change in velocity from time 0 to time 10.
Getting there.
Okay? So when we integrate, we have found a change in something. We found the change in velocity from time 0 to time 10. So if we already had a velocity of 3, then the velocity is then 88.
So were you integrating the acceleration there?
I was integrating the acceleration points. Yep, I plotted the acceleration points.
Isn't change in velocity the same thing as acceleration though?
Change in velocity over change in time is acceleration.
Travis over
But we
there.
don't have velocity. So if we had velocities, we could do change in velocity over change in time to get acceleration. But we're working backwards here.
Okay.
We're going to add another column into that chart. That third column we're going to call velocity. And we were just told in the problem that at time 0 we had a velocity of 3. And we just calculated that we have a velocity of 88 for time 10.
That's pretty impressive.
Meters per second.
Meters per second.
That's quick. That's speed.
Question number 2 says, in the table above, put in the column showing the velocity at the end of each 10-second time interval. So we would then need to repeat this process for all of the rest of the data. So we don't actually have to draw out all the pictures, but for the next interval of data, I would want to do 1/2 times 12 and 11, and still a 10-second interval. So-
165.
So that's, what is it?
165.
No.
No,
115.
Oh, yeah.
And that is, again, a change in the velocity. So we need to add that to our last answer of 88 to get a 203.
Are you
Does
sure
it
it's
say what-
115? Oh, it's yeah, it is.
That's what I have written in my notes, and I
Okay.
usually use a calculator when I do these.
Yeah,
So
Does it say what
I
kind
see
of-
what
vehicle
kind of
this
road
is?
Wasn't it 3
What?
Does it say what kind of vehicle
That's
this is?
23.
Oh,
what kind of what it is?
See, I did the same
Oh,
thing
no.
you did.
Because this thing's cranking.
It's not a vehicle.
5 times
it's an
23 is
object.
what the.
It doesn't say. It just says object, yeah.
it's a car.
There's no way
Yeah.
parking all that
Couldn't we
quick.
do like the big thing where you
That's
add
not like
them all
a-
up?
that's
So
one
like
thing I really like.
That would give us a beginning to end value, but it wouldn't give us each intermediate value. So if we want each intermediate, then we have to take each one individually. I'm just going to run through and plug in the rest of them here for us. So we end up then with
No.
238, 153, -12, and -112. Because in the next interval, our acceleration becomes negative, so those changes in velocity start decreasing.
How does it go to 238 right away though? Because isn't it supposed to be that answer will be 35? Oh, that never mind. I got it. Yeah. Okay.
Question number 3 on the sheet then says, assume that the average velocity in each time interval is the average velocity at the beginning and the velocity at the end. So we can take the averages of the beginning and the end. So typically they're saying it's really unsafe mathematically to take an average of averages. Okay, that's really a very dangerous thing to do. For example, I have 2 sections of Algebra 2. One of them has 19 students, one of them has 29 students. So if I would calculate one class's average on a test and the other class's average on a test and average those, that's not really the average of all of my students because one of those classes has a lot more students in it. Okay, so it is a dangerous thing mathematically to average averages. But in question number 3, they're saying, let's just pretend like we can average averages. Says, assume also that the displacement is 0 when time equals 0. So that we're starting with an initial position of 0. Show how the displacement can be calculated at time 10 seconds. So if I had acceleration data and I wanted velocity data, I integrate it. If I now want to get to position data, what do I need to do? Integrate again, but we'll integrate the velocity data. So I would do 1/2 of 3 plus 88 over a 10-second interval.
So 5.
And I get 455. I don't need to add anything to that. Oops, that doesn't go there. Initial position is 0. After 10 seconds, we're at 455
Yes.
meters. So yes, this thing is really traveling at 455 meters in 10 seconds. Maybe that's really traveling. I don't know. I don't speak
That's
in.
cooking.
Okay, I don't speak in meters. I'm very American.
Wait, what?
That's incredible.
Oh, that's really fast.
Wait, 455?
455.
meters per second. That's
Not meters per second, no,
At
meters.
about
In 10 seconds.
140
Oh,
miles.
that's
that
Yeah.
thing's going.
But like.
So question 4 then says, in the table, put in a column that shows at the end of each 10-second interval. So we do the same thing. So again, for the next one, I would want to do 1/2, 88, 203 over 10 seconds.
Oh, I'm gonna do this one.
And I would want to calculate whatever that is and add to it my last answer. And I didn't write down my intermediate work here.
13.25.
So
Is it 291?
the final answer is 1910. I don't know what that intermediate blank is.
1455.
Oh. What? Oh yeah, I'm wrong. 1450. That's not 1450.
Let's see.
I'm
Yeah.
confused.
Yeah, it is.
Use a calculator,
I'll
guys.
do calculator style.
I'm just copying down your stuff.
Yeah. Yes.
Yep, I was right on that.
I trust you.
What'd you say, Daniel?
1455.
Yep, you're right.
Question 5. Explain how you can tell that sometime between time 0 and time 60 the object stops and begins going backwards.
the velocity.
Because of
starts decreasing.
that one theorem, that's IMT or whatever. That
The
has
intermediate value theorem.
To, yeah, has to pass that.
We have to pass 0. So at some point our velocity passed 0. We have positive velocities, we have negative velocities, so at some point between time 40 and time 50 this thing started going backwards.
Yep.
Okay? Because the velocity became negative in there. Does the object go far enough backwards to go back beyond its starting point? How can we tell?
If the position is negative.
Okay, so we'd want to look at that final position. We can see we were increasing up to 60, 70, 6775, but then it did decrease down to 6155, but that's still 6,155 meters beyond its starting place. So it went backwards, but it only went backwards a little bit compared to how far it had gone forwards.
miles is that? Like 1,000 miles?
And our favorite last question, what did you learn that you didn't know before as a result of doing this? Hopefully not too much because we've talked about position and velocity and acceleration a lot. So this was more of a review exploration
I learned
than an initial learning
I
exploration.
learned velocity is the integral of